Hello and welcome to today. Hello and welcome to today's Code Presents. My name is Philip Bauer. and I'm excited to guide you through the process of using Azure ML Studio to create your own machine learning models. Let me share a bit about myself. I am a senior software architect at Code Consulting. Over the past 15 years, I've worked in various domains ranging from front-end and back-end development to server administration, deployments, and DevOps. Currently, I collaborate with our clients to integrate machine learning models seamlessly into their applications. If you have any questions after today's presentation, feel free to reach out to me at the email address provided here. Now let's take a moment to discuss the Code Group. Code has been dedicated to helping individuals and organizations build better software for an impressive 30 years. Our approach utilizes the expertise across our 4 divisions: consulting, staffing, training, and our magazine. In the consulting division, we offer custom software development, Copilot development, AI solutions, GPT implementations, and leverage our extensive Azure offerings. We also specialize in project rescues and modernization efforts, alongside providing ongoing support and maintenance for existing applications. If AI consulting services pique your interest, I recommend exploring our new executive briefing offer. In these briefings, we demonstrate how your organization can effectively leverage modern AI technologies in its applications. For more information, please visit the links displayed on your screen. I also want to highlight our exceptional staffing offerings at Code Staffing. Our staffing division is revolutionizing the industry by prioritizing the well-being of our employees. We ensure that our staff enjoys full benefits as employees, not contractors, which has led to rapid growth and employee satisfaction within our staffing division. If your organization has staffing needs, please visit codestaffing.com to connect with us. And for those interested in joining our team, we're always on the lookout for talented individuals to apply. Let's outline what we will cover in today's session. First, we will explore the reasons behind training your own model. Then we will provide a brief overview of the types of models available for fine-tuning and customization. After that, we will dive straight into a demo using Azure ML Studio to build a model capable of detecting solar panels in aerial photography. While conducting the demo, we will examine the project requirements and assumptions, learn how to select the right model, gather and prepare data, train and evaluate our models, and finally deploy our models using Azure ML Studio. So why would you want to train your own model? First and foremost, customization and optimization are key advantages. By tailoring a model specifically to your needs, using your own data, you can enhance its performance and accuracy. Additionally, you gain full control over the model's architecture and hyperparameters during training, allowing you to integrate your unique domain knowledge. When you work with your own data, you have the flexibility to pre-process it to achieve the best performance. Also, you have the ability to implement the model in a production environment of your choosing, minimizing the recurring costs associated with off-the-shelf products. These factors culminate to provide you with a competitive edge. Having a proprietary model designed for your specific requirements can distinguish you from your competitors or empower you to offer unique solutions as a third-party provider. Let's take a moment to explore the various foundation models available to you for fine-tuning based on your specific data requirements. Several classes of models are at your disposal. First, we have computer vision models that encompass a wide range of tasks, including image classification, object detection, segmentation, and even generative AI tasks like transforming text into images and vice versa. Additionally, there are models designed for video analysis and 3D object handling. To clarify when we refer to computer vision models, here's a breakdown of what you can expect. Classification models to identify what is present in an image. Object detection models specify where something is located within an image. Segmentation models that distinguish between groups or individual instances of objects in an image. And generative models utilizing AI to predict image depth or create images based on textual descriptions. Furthermore, we have natural language processing models capable of handling text classification, feature extraction, and even text generation, like to what ChatGPT does. All solar panels in an aerial image. Think along the lines of Google Maps imagery. For this scenario, we will operate under the assumption of limited hardware resources during inference and a modest initial dataset, which is typical for those just embarking on their machine learning journey. Now, how do we select the correct model? There are several key factors to consider. First, let's re-examine our problem statement. We want to detect solar panels in aerial photography. We must determine whether we require a generalized model that can identify multiple categories or a specialized model trained on specifically for one category, in this case, solar panels. Moreover, we must evaluate the complexity of the model against its performance. A generalized model may be larger and more complex, potentially sacrificing performance, while a specialized model can be smaller and more efficient. This will likewise influence the resources required for training. Your domain knowledge, meaning your knowledge about the data and desired outcomes, plays a crucial role in this decision-making process. Finally, we must consider the model's deployment and integration in your intended product. Now let's delve into the various machine learning models architectures. Understanding the differences between these architectures is vital for selecting the most suitable one for your use case. The first architecture we will discuss is supervised learning. Supervised learning relies on labeled data to generate predictions or classify new data. For example, consider an image with a bounding box surrounding a dog. This labeled data allows the model to identify similar categories or objects in future images. Next, we have unsupervised learning models. These models independently identify patterns and relationships using unlabeled data. They leverage inherent structures present in the data to learn effectively. Then there are reinforcement learning models. These models operate based on a set of rules tied to a predicted outcome or goal, rewarded when they successfully reach that goal. For instance, a chess model utilizes the rules of chess to learn the optimal path to achieve checkmate. In our case of identifying solar panels in aerial photography, we will employ a neural network utilizing supervised learning. But what are neural networks? Neural networks are structured machine learning models composed of multiple layers with trainable variables. You can think of them as similar to a Plinko game. Input is fed at the top, and it navigates through various layers, ultimately producing a specific distribution of outcomes based on the variables processed along the way. By training these layers, we can ensure they respond appropriately to a given input. Among the types of neural networks, we have feed-forward neural networks, which are commonly used for classification tasks such as spam detection. For instance, if we train a feed-forward neural network using a set of structured emails with known classifications, spam or not spam, the layers will learn to reliably identify spam messages. Next, we have convolutional neural networks, or CNNs, which are specifically designed to analyze grid-like structures like images. CNNs utilize convolutional kernels to simplify input data, making it easier to detect specific features within an image. This architecture forms the backbone of most computer vision models. Recurrent neural networks, or RNNs, on the other hand, are tailored for processing sequential data, such as text, speech, or time series information. We may also encounter combinations of these networks in applications, enabling us to optimize tasks like image segmentation. In our use case, we will primarily focus on convolutional neural networks. Let's shift our attention to another type of neural network, transformers. Transformers are fundamental to most modern generative AI models, including those used for applications like ChatGPT and DALL-E. There are three primary kinds of transformer models. The first type is the encoder-decoder transformer model. This model consists of an encoder that processes input and a decoder that generates output sequences. It is commonly used for tasks such as machine translation, text summarization, and image segmentation. Next, we have encoder-only transformers, typically employed for classification tasks. And finally, decoder-only transformers are used for generative tasks, including text and image generation. Encoder-decoder transformers can also be utilized for image segmentation, providing us with valuable candidates for our tasks. One promising option is the mask-to-former model, which features a convolutional backbone to extract images while employing a transformer architecture for processing and predicting masks. This model excels in handling overlapping features effectively. To illustrate, if two instances of an arm overlap in an image, mask-to-former has a strong chance of accurately detecting both instances of one arm. It can reliably detect continuous instances of an object, even if partially obscured. However, it's important to note that mask-to-former requires a substantial amount of training data and significant computational resources. It may also struggle with very small or very large objects. On the other hand, the mask-RCNN model, which is based on the convolutional neural network, is known for its speed and in detecting objects, but may have difficulty identifying overlapping instances. Given our goal of identifying solar panels in aerial photography and our constraints regarding limited computational resources, the mask-RCNN model is the more suitable choice. We don't expect overlapping instances of solar panels. Now, where can we find these models? This is where Azure ML Studio shines. It features a model catalog that allows you to browse and find specific models tailored to your use case. You can scroll through the drop-down menus to locate image segmentation models, including both the mask-to-former and mask-RCNN networks. Additionally, each model comes with a model card providing insights into the expected inputs and outputs. This allows your team to begin working with the appropriate data while another team trains the model. Let's discuss the steps necessary for preparing your data. First and foremost, ensure that your data meets specific characteristics. Relevance is crucial. Your dataset must encompass various representations of solar panels or your respective data, whether mounted on rooftops or on the ground. Diversity is also essential. Your dataset should feature solar panels in different scenarios, from sunny weather to rain and snow. This ensures that your model can correctly respond to various conditions. Furthermore, the volume of your data matters. A dataset that is too small may hinder the model's ability to accurately predict solar panel locations. You will also want to maintain a balanced distribution. For example, if your dataset has 80% sunny day imagery and only 20% of other weather scenarios, it could lead to the model being overtrained on sunny day images and inadequately prepared for other conditions. Additionally, the quality of your content is paramount. Opt for high-resolution images, as high as possible for the model. Low-resolution images, such as those sized at 128 by 128 pixels, provide insufficient information for effective training. Conversely, larger resolution images offer more data for analysis. And above all, the quality of your annotations must be high. As we will see during the demo, poor annotation quality can negatively impact the inference output. Here are some potential data sources you can consider for your dataset. There are public datasets available on platforms like Kaggle or RoboFlow, which may serve as a good starting point. You could also utilize crowdsourcing to obtain annotations or conduct in-house data collection. Some marketplaces offer datasets for purchase, and if legal and appropriate, web scraping techniques could provide additional data. For annotation, consider using tools tailored to different scenarios. General purpose tools like those integrated into Azure ML Studio or software like Label Studio are effective options. But you may also find specialized annotation software for computer vision, audio, or language processing tasks. Now let's visualize how annotations might appear. This image here from our dataset showcases some overlaid annotations. As you can see, the annotation quality here is questionable. For instance, in the bottom right corner, the edges are not quite straight, and solar panels typically have straight edges, making this annotation inaccurate. Moreover, in the top corner, it's evident that the annotator neglected proper outlining, which will likely affect the inference result. So, how can we annotate our datasets using Azure ML Studio? In Azure ML Studio, you can select the data labeling option and utilize the wizard to create a new project. For our project, we choose the image media type and the instance segmentation task. I'll select a dataset imported from Kaggle that includes images and annotations as we just reviewed. As we navigate through the wizard, we add relevant label names and enable or disable machine learning models to assist with labeling. Once the data is imported, we can approve or reject specific annotations. A significant advantage of the tools available in Azure ML Studio is the ability to make corrections directly within the platform. This eliminates the need for back and forth communication with others for minor adjustments. In these examples, I will refine the annotations and approve them. After completing the annotations, we can return to the dashboard for an overview of our progress before beginning to utilize our dataset. Now that we have our annotations in place, let's set up our dataset for training. By selecting the Data option under Assets, we create a new data asset. Here, we'll provide a name, description, and select the correct type, tabular in this case. We can then choose where to pull our data from. Here specifically from our Azure storage. I'll select a file called annotations.jsonl, which is a specific format for multiple JSON objects in one file. It is vital to ensure that we correctly define the data types. For images, we want to use the stream type. Using the stream type indicates that we want the underlying data, not the URL string itself. And finally, we can preview our data to confirm it's correct, and upon approval, we can move forward with training and evaluating our model. Next, let's discuss the considerations involved in model training. First, it's essential to split your dataset, followed by training and evaluating your model. During this process, we need to meticulously track all of our experiments. What does it mean to split your dataset? How do we prepare it properly? One crucial step is to shuffle your data to prevent bias from clustering. Datasets often inadvertently become grouped, so shuffling ensures a more even distribution. When splitting your dataset, size matters. For small datasets, allocate a larger portion for training and a smaller portion for validation, and vice versa. For larger datasets, you can grow the split in favor for the validation. This ensures that some data is available to evaluate how well the model performs on unseen data during training. You can also augment smaller datasets through various modifications, such as rotating, skewing, or flipping images, which can enrich your dataset for better model training. Alternatively, you might consider generating data from scratch. For example, a project involving Lego pieces used 3D models that were rotated and colored to create images, resulting in a diverse dataset. This was then used to identify 3D or Lego pieces on a conveyor belt. To train your model, it is crucial to set appropriate hyperparameters, encompassing settings that influence the training process. Key hyperparameters include training duration, iterations, or the number of times the model sees the data, and learning rate, the degree of influence each iteration has on model values. You might also consider batch size, where multiple images are processed simultaneously to aggregate their effects on the model parameters. Automating these training processes using preset parameters is highly recommended. Always modify one variable at a time to ascertain the impact of each change. If you alter multiple parameters simultaneously, identifying the cause of any observed effect becomes challenging. Now let's take a look at how to initiate an automatic machine learning job in Azure ML Studio. Simply navigate to the Automated ML section and start the training for a new model. Select the computer vision tasks such as polygon or instance segmentation and choose the dataset we just set up. Then designate the target column, specify the number of trials to run, and determine how many concurrent tasks to perform. This sweeping process will define all hyperparameters and their changes. You can opt for automatic settings or manually adjust them according to your preferences, like I do, selecting one base model with a smaller network with fewer network layers and one with more network layers. Finalize the configuration and select the type of compute you want to employ, whether a serverless option or a previously set up cluster, and then start the training. As Azure ML takes over, you can observe the overview pages where the status progresses from not started to running and eventually to finished. Upon completion of your model training, it's crucial to evaluate its performance. This can be achieved through several methods. One option is manually inspecting the predictions generated by your model. For instance, I ran some tests, allowing us to compare outputs against the ground truth or the labels fed into the model during training. On the left-hand side, you can see the ground truth, followed by model outputs after 1500 iterations, 500 iterations, and 100 iterations. As we progress from a higher number of iterations to a lower, we can observe how the model's ability to detect solar panels degrades substantially. With the lower iteration count, we see it does not find any solar panels at all, but it does a pretty good job with the higher iteration count. and respectively the larger model is doing a better job than the smaller model. Another method involves monitoring metrics that contribute to the creation of learning curves. What are learning curves? During the training process, the algorithm computes what is known as training loss. This encompasses both training loss and evaluation or validation losses. As mentioned earlier, regarding dataset splits, one portion is designated for training, while the other is used for evaluation. We can plot these loss curves to observe their progression. Ideally, we want them to minimize loss. For example, the training loss might start at approximately 2.5 at 0 iterations, progressively decreasing with additional iterations, as we can observe here. You'll also typically want to track metrics such as average precision. This metric assesses the overlap between the predicted mask generated by the model and the ground truth mask. One interesting observation is that with the model featuring fewer layers, we can see it starting to flatten out after 1500 iterations, signaling an opportunity to enhance performance by possibly utilizing a larger network structure for further training. We can observe this in the larger underlying structure, with the model with the larger underlying structure, that the precision continues to increase, indicating that the model is still learning and we could use further iterations to get better at detecting solar panels. As we train our model, we have to look out for the potential issues of underfitting and overfitting. Overfitting can happen when a model learns noise or irrelevant details within the training data, affecting its ability to generalize. It will present as a divergence between training and validation loss. On the other hand, underfitting may occur if the model is too simplistic for the complexity of the data, or if the data quality is inadequate. The plotted loss curves will show a high loss value for both training and validation data. A well-fitted loss curve is one where both training loss and validation loss follow a similar trend. To review metrics generated during training jobs in Azure ML Studio, we can navigate to the Jobs section and select the specific training job. Here you can view various metrics and visualize the learning curves we discussed earlier. It's vital to keep track of all of your experiments, whether using Azure ML Studio or other platforms. Azure ML Studio simplifies this process by retaining experiment data, but it's advisable to have your own system of referencing previous training experiences. Be sure to version your datasets in relation to your trained models and save all relevant metrics generated throughout this process. And remember, the difference between scientific method and screwing around is writing it down. Now let's turn our attention to deploying the model. Deploying can be intricate, depending on where you run it. For instance, in Azure, you might need to configure a Kubernetes cluster with GPU-enabled instances. However, Azure ML Studio streamlines this process significantly, allowing you to complete the setup with just a few clicks. To deploy our model, simply select the desired model and click the Deploy button. From there, you'll navigate through a wizard to choose your virtual machine instance and specify a desired amount of instances. In my example, I'll select a GPU-enabled instance and assign an endpoint name and a deployment name. And then I hit the Deploy button. After a brief wait, your virtual machine will spin up and be ready for inference. Upon completion, Azure ML Studio will also provide a snippet of demo code for your deployment, which you can review and utilize in your application development. You have the options for authentication, such as using an API key or Microsoft Entra for endpoint authentication. For instance, in this demo code snippet, the inference output will yield a polygon mask that can be overlaid on the input image that we send to the endpoint. Running this output will demonstrate the solar panel masks. Now, it's important to note that any of these irregularities in these masks are stemming from the earlier mentioned annotation quality issues. You can see these are quite wiggly here. So again, pay attention when you do your annotations. One of the most important things. To summarize our journey today, we discussed the importance of training your model, highlighting how custom models can optimize performance and integrate domain knowledge for competitive advantages. We explored the available models, including computer vision, natural language processing, and audio models, and examined how to develop and select the right models based on data and use cases. We also reviewed the meticulous process of preparing datasets while emphasizing the significance of annotation quality. Finally, we discussed the training and evaluation of models, ensuring proper data splits and automation of experiments while capturing everything for future reference. Thank you so much for attending today's Code Presents. Please don't forget to subscribe and ring that bell to always get a notification when we release a new video on our CodeMag channel. And if you're not already a subscriber to our magazine, you can use the link on the screen to subscribe for a free digital subscription. And to everyone who is attending our Code Presents live, you have the chance to win a $100 Amazon gift card by simply completing our survey until end of Friday. Please let us know what kind of content you would like to see next. And with that, let's start our Q&A session. Hey everyone, welcome to the Q&A session. I see there are just one question currently. So the question is whether this will be available later on, and yes, we will upload this video again for consumption later on, and we will also share the slides in the description for this presentation. Since this is a little bit offset from the about 15 seconds delayed, I will just wait if there's any question still in the chat, and if not, we'll stop the live stream in a little bit. So if anyone has any questions, just let me know. So one question coming in is what the AWS cost to run the demo would be. On AWS, I'm actually not quite sure what the price structure is on there at the moment. For the demo on Azure though, the machine that we're using there costs about $430 per month for 24/7 use. It's a NVIDIA T4 machine, and that's the pay-as-you-go pricing. If you reserve an instance like that, for example, you'll save significantly depending on your reservation. If it's a 1-year reservation, I believe it was around $230, and I think just sub $200 per year per month if you reserve it for 3 years. Well, if there are no other questions coming in, thank you all again for participating in today's Code Presents. Oh, there's one more question coming in. we looked at detecting whether an item is available in an image. Which model would you recommend to detect forms like text and images? Example, detect vehicle registrations in images. That's a good question. So if we are talking about license plates, for example, we could use a model trained on license plates to locate the images. A YOLO type model, YOLO, you only look once, model might be able to be trained for that kind of task. And then you could use an OCR model to actually read the numbers and letters of the license plates in that image and then feed that into your application. There are several YOLO models available at the moment. I think the last one that was released was version 11. Some of these are available for open source use. Some are only usable after paying a license fees for them. What is my opinion of what's the better model to analyze medical data to predict the trend of a person's health? That is a little bit more complex because a diagnosis might consist of multiple things from different kinds of stats gathered through blood testing, all your doctor's notes, etc. I think that is something that needs to be carefully designed, specific to what you're actually trying to do. If it's analyzing blood values, you need a significant amount of data to detect trends. So that's a little bit more involved, especially considering that when we're talking about medical uses of machine learning models, you want to be very careful with that. Uh, is there any model to help with office automation? That's a very broad topic. Office automation in what regard exactly, Christopher? If we're talking, for example, what we're using, I just until you're replying, what we're doing internally is we're using a lot of large language models to process, for example, transcripts of our meeting recordings. That is one big thing that we do. So there's a one part of office automation. So any kind of office automation, all right, local government. So anything to help with email or documents. There are so Microsoft, for example, is already including their language models in their Office 365 products. They can help with analyzing emails to an extent. They also Microsoft offers a document recognition service in Azure. That is something that we, for example, use in an in-house application to analyze expenses. So, for example, we can when we travel, we can take pictures of, for example, a receipt from a restaurant, and this document recognition engine is then uh, set up so that it will recognize what the total value is and put that into our expense tracking. Those kinds of things. There are either services or different models available that can do that. In Azure ML Studio, you should be able to find similar models like that. Would you use AI for something like other customers also? Broad suggestions, that kind of thing, best done by just directly processing previous purchases. A other people bought kind of recommendation engine. Yeah, you could use models. You could train a model for that. That really is dependent on your data structure, I would say. This can also be a statistical model. It doesn't necessarily need to be a neural network for this kind of task. Um, Yeah, you're welcome, Christopher. Hope that helps. And if you have any questions, again, feel free to reach out to us either through our info at codemag.com email address, or just send me a message at pbauer@codemag.com if you have any further questions. We're always eager to help, and we won't charge you for just a simple 15-minute reply or something like that. We want to help everyone on their machine learning journey. All right. So again, I think there are no questions at the moment coming in. So I want to thank all of you again to for attending, and I hope that if you have any questions, you'll reach out, and we're always here and happy to help you all. Thank you so much.